Okay. طيب, بسم الله الرحمن الرحيم. Just to reiterate on this slide, so we talked about these 4 classes of service last time. The first 3 classes are for providing certain quality of service. The 4th one is for best effort for applications that do not require any quality of service. The first one is for fixed bitrate, constant bitrate. The other 2 are for variable bitrate. The 3 of them are for quality of service provisioning. The first one, in terms of bandwidth requests, the first one, the nodes or the subscriber stations, they actually request the bandwidths only during the maintenance periods, and they use some indirect or implicit way of bandwidth requests through what we call slip indicators. Whereas for the other 2 cases, we use unicast pulling. So these 2 methods, they use unicast pulling, in which case the base station will pull in a unicast, will pull the subscriber stations, and the subscriber stations will send their bandwidth request. In that case, this method does not use multicast bandwidth requests, multicast or broadcast bandwidth requests, which happens during the contention request period. Okay, but this method, it does allow the pulling, whether it's unicast or multicast, during the contention request period. So just pay attention to the differences between these 4 cases. Here, there is a little bit of a discrepancy here, because here it says that for best effort services, the bandwidth request is allowed through contention requests or piggybacking. Whereas here in the table it says all forms of pulling, which implicitly includes also the unicast pulling, whereas this is not allowed for the case of best effort. So for best effort, bandwidth request is through the contention requests or piggybacking only. But the unicast pulling is not allowed in that case. Okay? So just pay attention to that. So in terms of quality of service support, we talked about that. We said that we have 4 classes of service, so we can provide per class quality of service support. Can we provide per flow quality of service support? Does that include per flow? Well, yes. For 802.16, the connection, we said that the grants happens per subscriber station or per connection, right? So we can grant the time slots based on the connection. If we map different flows to different connections, then we can provide per flow guarantees. Okay? So per class is already part of the standard. Per flow is possible if you map the individual multicast, the individual multimedia flows into separate or different connection IDs. If you assign for each flow different connection IDs, which means that the audio has to be managed in a separate connection from the video. Okay? If that's the case, then you can provide per flow guarantees as part of the standard. However, the standard does not dictate a certain mechanism for how you schedule these flows, as we have discussed last time. Okay? So these are the 4 classes of service, and for classification, we said that both the connection ID and the subscriber stations will have to be mapped to service flow ID. The service flow ID will give you the actual class of service that can be provided to this connection or this subscriber station. So we can provide this at the level of subscriber station, which means that all the flows, all the connections that are coming from this subscriber station will have to be treated the same way. Okay? Or we can provide that on the level of the connection and give each flow coming from the subscriber station a different service flow ID, in which case we can provide per flow guarantees. Okay, so based on that, we tag whether the packets that are coming from the connection or the packets that are coming from the subscriber station with a specific service flow ID to indicate the type of service that we want for this particular connection or subscriber station. For the scheduling, we said that the downlink, it's easy because all the queues are centralized in the base station. Okay, so in that case, we can provide whatever scheduling we want based on the mechanism that is run only in the base station. Whereas for the uplink, it's a little bit tricky because the queues are distributed, in which case you can have any distributed kind of scheduling, okay? And this is not part of the standard. So the uplink scheduling is not actually part of the standard at all. And we talked about the provisioning model, which is, as I said, it's not actually very important, and it's based on the sequence of provisioning the quality of service from the start point where the subscriber station will have to register as a service provider with a particular service level agreement and stuff like that, and that will propagate in the system. So this is the overall picture now. So from the application, all the application level, whether the connections or all the traffic that is coming will have to be mapped through a classification stage to a particular connection ID and service flow ID. This service flow ID will actually assign a certain class of service to all the traffic that is coming with this service flow ID, and based on that we provide the service based on the class that this traffic is assigned to. So at the base station, the same thing happens. The signaling that is going back and forth between the two, because as we said, for quality of service mechanisms that we talked about, first we have classification, right? We talked about channel access mechanism. Channel access here is very clear. It's TDM in the downlink and TDMA in the uplink. So that's clear, right? The scheduling we talked about, we said that the actual scheduling mechanism is not part of the standard, okay? But what we know is that all the queues are centralized at the base station in the downlink, and the queues are distributed in the uplink. So we can provide whatever mechanism based on this architecture. So the remaining part is here, the admission control. So we talked about admission control and the quality of service signaling, the signaling mechanism. Well, the signaling mechanism we talked about in a way when we discussed the bandwidth requests. So bandwidth request is in fact the quality of service signaling. So bandwidth request is the mechanism for the subscriber stations to report their demands to the base station, and based on that we provide certain quality of service guarantees, right? So the bandwidth request, whether it's done as part of the initial maintenance phase or the contention requests or unicast pooling, or all these modes of operation, they facilitate some kind of bandwidth request from the subscriber stations to the base station, and therefore the base station will grant the time slots in a certain way that will provide the quality of service required. Okay. So so this is the channel access mechanism. So channel access is TDM and TDMA. It's clear. It's well defined in the standard. Okay. The scheduling, as we said, is not defined, especially the uplink one is defined. And the signaling mechanism here is the bandwidth request. But again, that does not mean that because you have provided the bandwidth request through whatever mode of operation, that we will dictate in the standard a certain mechanism to schedule the time slots. This is not defined. So this part is not defined. And also admission control is not defined in the standard. It's not part of the standard at all. But the question is, can we provide explicit admission control or implicit admission control? This is a guess or based on information? What is the condition to provide explicit admission control?
And as we have to accept to be explicit.
Which means that we need a mechanism to send information through the network to be able to have the information whether to admit or reject, right? Do we have this information? Yes. So the question is, can we provide explicit admission control? Because we have this information. Can we? Whether it's part of the standard or not, that's another question. So this question is well known. So we know that it's not part of the standard. But theoretically, can we have explicit admission control? Since we have explicit bandwidth request mechanism, which is the quality of service signaling, okay? Therefore, we have the information to know all the demands of subscriber stations. So from the beginning, we can just say, sorry, I cannot grant your request, I will reject your connection. Okay? So we can do that. It's not part of the standard. But we can do explicit admission control because we have explicit information from all the subscriber stations. So the explicit admission control is possible, but it's not defined. ماشي؟ مفهوم? It's possible, but it's not defined by the standard. So, which means that one of the vendors might say, okay, so I will use some admission control mechanism as part of my 802.16 network, okay, and accept or reject the requests that are coming from the subscriber stations at certain point in time to be able to guarantee good level of quality of service. They can do that and they'll still conform with the standard. We cannot say, no, you define something that's not part of the standard, so it does not. No, it's not defined by the standard. So just the fact that it's not defined by the standard, it doesn't mean that I cannot do it. Blacks, if it's not defined by the standard, I can do it and I still conform with the standard. Okay? So if there is any block that is not defined, a vendor might say, I will implement my own and I still conform with the standard. I will still be compatible with the standard. مفهوم النقطة دي؟ So if there is any part that is not defined in the standard, this doesn't actually mean that you cannot do it. Blacks, this means that you can do whatever you want here and you still conform with the standard. Okay? As long as you apply the bandwidth request mechanism in the exact same way that is defined in the standard, the way to use these bandwidth requests later on, it's up to you. That's what the standard says. So someone might take these signals and use it in a certain way, and whatever this method will be, they will still conform with the standard. Okay? So these are all the quality of service mechanisms that we talked about and whether they are defined in the standard or not. If it's defined in the standard, then we have to implement it in the exact same way that the standard dictates. Otherwise, we will not be compatible, we will not conform with the standard. If it's not defined, then it's up to you. Okay? So from what we have discussed so far, it looks like the admission control is not defined in the standard, so we can do it, and in fact, we can provide some explicit admission control in any way we see appropriate, and we still conform with the standard. Also, the scheduling is not defined in the standard, so we can provide our own, mechanism to grant these time slots, whether in the downlink or the uplink, in any way we see appropriate, and we still conform with the standard. Okay. Okay, so that's so we still have one small chapter. I think we'll probably next week we should be done. And so we'll leave enough time for people who have senior projects and stuff to wrap up their senior projects. And so this chapter, I actually shrunk this chapter significantly. So this chapter in the previous offering of the course was like 3 times what I have now. So I actually took one part only. And this would allow us to have enough coverage for 3 different categories of wireless networks. So at the beginning, we talked about Wi-Fi. We said that Wi-Fi is for local area networks. It covers an area, a geographical small area between multiple users. And Wi-Fi, as we said before, was originally designed for data. And that's why PCF was optional at the beginning, but then in 802.11e, HCF was introduced to provide some guaranteed quality of service, some per flow and per class quality of service. And therefore, Wi-Fi, at least 802.11e, is able to provide some guaranteed quality of service, and therefore we can have what we have nowadays. Luckily, we can have voice over IP and all of this, and it works efficiently on Wi-Fi. So that's good. The other category of wireless networks is metropolitan area networks, where the metropolitan area networks can be used as an internet access replacement. So we can connect directly to the cellular network, okay? And the metropolitan area network is meant to cover a large geographical area, okay, which is like part of a city, okay, like maybe 1 kilometer or something radius. And originally, this type of networks was designed for voice, okay? And that dictated the fact that from day one, these standards came with the mentality of not having any collision, okay? Because collision creates such a random environment that does not allow us to provide guaranteed quality of service, or what we call circuit switching like connections, where we can provide some guaranteed quality of service for voice calls and so on and so forth. But again, later on, these metropolitan area networks, they provided some special services for data as well, which is what we have nowadays, like 4G and data plans and so on. And this is dictated by also the quality of service part that we talked about. This part, or this chapter, talks about a 3rd category of wireless networks, which is concerned with wireless personal area networks. So this is a wireless network which is meant to provide communication for one person, mainly one person. So we have multiple wireless devices that all work hand in hand to provide a certain service for a person. That's why we call it personal area networks. Okay. So this is meant to work in a short range radio, and because it's personal area network, it's also meant to be very low cost. We did not talk about the cost issue in the other 2 categories of networks, right? Because in these categories of networks, devices are relatively heavy duty, so we have like our mobile, and we can have some sophisticated hardware in our mobile, and it's high cost, relatively high cost. But here in personal area networks, we talk mainly about devices which are very low cost, like headsets and very small, tiny little devices. This also includes like some sensors that work for healthcare, like ECG and EEG and these kind of small, low-cost sensors. And of course, the most famous standard for this is a Bluetooth. بالظبط. So that's the chapter where we talk about the Bluetooth standards. So we need to talk about Bluetooth as a standard, and we'll see whether Bluetooth was designed whether for data or for voice or for both, or whether it provides certain quality of service, and what are the mechanisms that allows Bluetooth to provide quality of service. What are the quality of service mechanisms that are there, whether we have specific channel access mechanism, what is the channel access mechanism, what is the scheduling mechanism that we have, whether we provide admission control, explicit, implicit, things like that. But the main thing here is that this is meant for very low range, very small range communication, okay? And it's built or designed with cost in mind. So these devices need to be very small, which means that it has to be energy efficient. Okay, so if you put these high-level characteristics in mind, this will dictate certain characteristics on the design of the radio layer, on the data link layer, and on the higher layers, which is what we need to discuss here. ماشي? Okay. So wireless personal area networks, it works for short range, although short range is like 100 meters, which is relatively very far, and it really these types of networks, because these small low-cost devices are sometimes used for remote sensing. Okay, they still categorize it as wireless personal area network, although the range 100 meters is not really that short range. But this can get as low as sometimes like 10 meters or maybe less. Okay, and when we talk about 10 meters, this doesn't mean that you can get actual 10 meters or even 100 meters. That doesn't mean that you can get one. This talks about the range in vacuum, where you have no air. So the air actually blocks the wireless signal. So the actual range that you get is probably maximum like 90% or 95% of this. So you can almost never get the actual 100 meters, except that if you are in a vacuum. Okay. So, but the important thing is that these are meant to be very low power. This is the first time we talk about low power and low cost, which means that we need to care about how lightweight the mechanisms that we talk about are. Okay, that's also another thing that we did not talk about. Okay, because this will dictate how the network is designed. And relatively small networks where you have small number of devices. So we can use that characteristic in our benefit when we design the protocol. Because if we know that the number of devices that we communicate with are low in number, then we can use that to make the protocol lightweight. Okay? So Bluetooth is the most common standards. Of course, there is ZigBee, and there are some other standards which we will not cover. We covered last time, but we will not cover here. Which makes sense because Bluetooth is the predominant standards in that category of wireless networks. Even ZigBee is almost dying now. So Bluetooth is 802.15.1. Okay. Originally, Bluetooth was designed with a consortium of companies. Okay, they came together in a consortium, and they actually defined Bluetooth standards. It was not part of 802 family at all. They defined their own standards, and at this stage it was what we call proprietary standards. Proprietary, which means that it's not an international standard. However, 802.15 group, they tried to define what they call a standard for low-range communication or small-range, small network communication, and they have identified Bluetooth as a complete match for the requirements of what they want to come up with. So they adopted Bluetooth. And since then, Bluetooth has become the international standards for 802.15.1. Okay, so they had a shortcut. So usually what they do is that they define the requirements, and then the requirements would go to the companies or to the stakeholders, and then the stakeholders will take these requirements, will try to come up with a specification. Bluetooth is one of the standards that actually work the other way around. So the companies first, they define the specs, they came up with their own proprietary standards, and then 802.15 they adopted it. Mashi? Not that it makes any difference for us, but this is like a historical, and they say that Bluetooth is named after like an old king in Denmark, and because he had like some toothache or something like this. Does not concern us. So anyway, so this is the architecture of the standard. So basically, 802.15.1, it works in the ISM band, so 2.4 gigahertz, and we said that this is the most common band because all the manufacturers who actually design wireless devices in this range, they don't have to pay the license fees or something like this, which is attractive. However, this makes this range very condensed and very crowded, and that's why in this range you usually have relatively high level of interference from multiple devices. Okay, and that's one of the things that in the radio layer, in the physical layer, you have to implement some mechanism to mitigate such interference, and this is the frequency hopping. So we talked about frequency hopping in 802.16. So we said that frequency hopping is one of the ways to mitigate interference by changing the frequency. So if you have interference high in certain frequency range and low in certain frequency range, this way this is not to eliminate the interference. This is only to balance out the interference. So if you change the frequency range, this means that you get at certain point you get high interference, but in certain point you get low interference. So overall you are balanced in terms of how much interference each part of the network gets. Unlike, and actually the hopping here is you have 79 hops, which means 79 frequency range. You hop through one of them. Okay, so you have 79 that you have to jump back and forth, and the hopping is very high frequency. It's up to like 1600 hops per second. So we'll talk about that. It uses what we call Gaussian frequency shift keying. So unlike 802.16, remember for 802.16, not sure if you remember, but for 802.16, we talked about different modulation schemes. We said that we can use QPSK or 16 QAM or 64 QAM, and we can have what we have called the adaptive burst profile, where we can change in each frame what modulation we use, right? Here we don't do that. Here the standard dictates GFSK as the modulation scheme. Okay? So that's how to relate the standards together. Sometimes there is a reason for these design options, because these are design options, right? These design options might reflect on the hardware design, and it might reflect on the cost, and so on and so forth, right? So that's why you have to make your design choice carefully, right? One reason could be that for 802.16, we work on a very large range of communication, right? In this large range of communication, the channel itself changes a lot. The variation in the channel up and down, so the path loss changes drastically, right? So changing the modulation is a very key mechanism to increase or decrease or to adapt to the different probability of errors when the range is very long. Here the range is short, therefore the channel does not change that much. So there is no point of actually providing multiple modulation scheme, especially that providing these multiple choices of modulation scheme will complicate the design of the hardware, right? So there's no point, okay? So yeah, that's why I'm trying to give you some idea. When you make the design choice, sometimes you have to think carefully about the characteristics of the entire system before you take one choice over the other, okay? So you can have, for personal area network, usually you have your own, what we call piconet, okay? So a piconet is actually a small network which is composed of one master and multiple slaves, okay? And someone might say, I mean, why do I have to have master? I never had to configure my Bluetooth device as a master or a slave. Well, that happens in a very low level, but it's required. Why? It's required to simplify the control and the access to the channel. Because if you don't have a controller to the channel, the access to the channel becomes very challenging. And as we have discussed before, if you don't have a main controller, then you have one of two choices. Either you randomly access the channel, in which case you end up with collision, or you predefine the time slots, which will make the system very rigid and will not be efficient in that case, right? So that's why in many standards they opt to using a centralized controller to simplify the access to the channel. So in any case, so you have a piconet, you have up to 8 different devices in one piconet, which limits the number of devices in the piconet. And that's meant, as I said, to make the protocol lightweight. But the standard also defines what we call a scatternet. A scatternet is a multiple piconets connected together, okay? So one device can be part of 2 piconets, okay? So this device can be a slave in one piconet and a master of another, okay? Or a slave here and slave here. Although the most common one is that it's a slave here and a master here. It cannot be a master in both, because if it's a master in both, this means that the 2 are one piconet, okay? Okay, so that's the high-level architecture. So just the fact that we have up to 8 devices, that doesn't mean that the standard also only allows communication between 8 devices. So we can have more than 8 devices, but in that case they will be communicating through multiple piconets. So you will have 2 hubs. So within one piconet, always the slave communicates with the master. Similar to all the standards that you talked about. So we always communicate to the access point. So even if one slave wants to talk to another, it has to go through the master. If one slave in here, if this one wants to communicate with this one, it has to go through the master, and then from here to the master, and then from here to the slave. So it has to go this way. Okay? So the range, this range is allowed to be up to 100 meters. So within 100 meters, you can pair the 2 Bluetooth devices together. However, as I said, this is the theoretical range, and what you get actually in practice is much less than that. That's the layer stack for Bluetooth. And we can sort of try to identify where the physical layer is and where the data link layer is. And the boundary is a little bit fuzzy. But we can easily identify that the physical layer is this part, and this is the data link layer, which includes a baseband or link controller and these higher layer devices, higher layer layers, which we will talk about in a bit. So this part is hardware, which means that part of the data link layer is done in hardware, which is what we are familiar with. So as we said before in 455 and in other courses, physical layer is purely hardware. Data link layer is the first layer where we have like some hardware with embedded system, with some embedded systems or some software algorithms that have to run on the hardware. And then the higher layers will be purely software. Okay. So very quickly, of course, in the physical layer, this is where the carrier frequency 2.4 gigahertz and the frequency hopping happens in the radio layer. So we talked about that. Here in this part is where we have the MAC layer. So the baseband link controller is where the channel access mechanism, which we will talk about in a minute. And here there is a link manager. And the link manager, this is the one that sets up the link between two devices. So at the beginning, you have, so this is sort of like the logical link control sublayer. You can think about it this way, where if you have a master and a slave, or a master and a master, and you want to initiate a communication, so the slave will have to send like some connection first, because here this standards provides services, mixed services between data and voice. So you in some cases you have some setup for the connection, so it's connection oriented. So you have to set up and tear down connections. So that happens through the link manager. So you can set up and tear down connections through the link manager block. So the host control interface, you can think about it as like the management entity in the. So this is where the where you can control this hardware. You can control like the channel and the frequency and all of the parameters of the hardware. So you can think about it as it's the management entity in the previous standard that we talked about. This is called the logical link control and adaptation protocol. So this is a new sublayer. We did not talk about it in any of the standards. And the reason here is that Bluetooth was actually designed for both data and voice or multimedia. So from the beginning, these devices, or the Bluetooth devices, can be used for data communication or for voice communication. So that's why in the standards, they initially tried to incorporate this in the layer stack. And the function of this logical link control and adaptation protocol is to try to adapt and interface the higher services to the lower data link layer functions. Okay? So as we will see here, these are different types of services that can be provided by Bluetooth. You can have the route of audio, and of course this includes multimedia communication, multimedia streaming. So in that case, we use connection-oriented and synchronization of communication, or what we call synchronous connection-oriented communication. We'll talk about this later. So in here, you need to provide guaranteed quality of service, and you need to provide circuit switching type of communication. Circuit switching, which means that you need to set up the connection and before you have communication and so on. So this is this route. Or you can have different types of services. This is, for example, this is a radio frequency communication, and this actually emulates, you know, the USB. USB uses like serial communication. So you can use USB over Bluetooth. So Bluetooth can actually emulate serial communication for you. It's as if the device is connected through USB. Okay? So to do that, this logical link and control adaptation protocol will have to convert from the serial communication to the channel access mechanisms and all these things. Okay. Similarly, of course, you have TCP/IP type of communication, and you have some other services which we will talk about later. But basically, this logical link control and adaptation protocol will map the high-level services into data link and physical layer functions. Okay, and because the high-level services are diverse, and they can provide circuit switching and packet switching, so we need some layer in between to adapt or to customize or to do like some packet segmentation or something like this to adapt the high-level services into lower layer functions. So this is the high-level description of these blocks, but we will spend more time to explain the function of each one. So, okay, probably next time.